has to be the respective voltage and current. Like when you're talking about the positive sequence impedance, only positive sequence voltage and positive sequence current are being referred to, no other. That's what I was trying to mention, that they are independent of each other, and they are also called that mutually decoupled. They don't have any coupling in between them, meaning they cannot affect each other. Like when you talk about those transformer, primary winding, secondary winding, they are mutually coupled through the electromagnetic induction process via the core of the transformer. In this case, is independent, each mutually decoupled. So we will use positive sequence impedance, negative sequence impedance, and zero sequence impedance for our asymmetrical fault analysis. Of course, it also applies for symmetrical fault analysis, and we will need to know such impedances for our power transmission line, for our motor, for our transformer, for our generator as well, and that is where we will go in a step-by-step manner. So let's go to the next slide. I'm going to the power systems components. That's what I just mentioned. So in our power systems, this is another classification from another perspective. It's a broad one. Is what are the components or the equipment that we have in our power system? If we look at them, we find that some of them are static. They don't have any rotating or moving parts in them. And those are transmission line, transformer, and static loads. They don't move or they don't rotate. They don't have any moving parts in them. And examples are shown on the slides. Transmission lines, they are static. Transformers are also static. Also, they move or vibrate because of that electromagnetic phenomena that happens due to application of alternating current to the primary winding. And then static loads, they are also static, they don't have moving parts. But we also have another big section, or the machines that rotate, they have moving parts. Like we have synchronous motors, synchronous generators, induction motors, induction generators, and we find that they are a bit complicated as compared to the static components or the equipments that we use in power systems. And complicated means when you look at those three impedances, positive, negative, and zero sequence impedances, we will find them very interesting or easy in case of static components like transmission lines and static loads, but not that easy in transformer. But for rotating machines, it's different. We might have three different values of positive, negative, and zero sequence. They don't necessarily need to be the same, and it also depends on what are we interested on. For example, if you want to study a synchronous machine, and you will not need to know for how long, what is the duration of your study. Is it very small time, is medium, moderate, or it's a long duration that you are looking for, like steady state analysis. For steady state analysis, like we did in our load flow studies, it's a steady state analysis. We want to look it for a long duration of time. So those time duration of our study will also determine what will be the impedance, positive, negative, and zero sequence. So let's go to that one and we'll see what happens. Now, I mentioned and I showed you some sequence networks that we have to draw, and we draw them from the current, voltage, and impedance equations. Current, voltage, and impedance equations. And again, just to remind ourselves, they are independent of each other, meaning there will be three different voltage, current, and impedance. So three different networks: positive sequence network, negative sequence network, and zero sequence network. And we use to show a single network using a voltage source for positive sequence and an impedance, and showing the respective polarities, the current, voltage, and impedance to that particular sequence network. So if it is positive sequence network, we will draw it like this. So it will look like that. It will have a voltage source. It looks like a Thevenin's network, a single voltage source with the single impedance, which is Z1, and it has to be Z1 because it's positive sequence network, and it has to be shown here as N1, which is the reference bus or the neutral bus, and it has to be N1 because it's positive sequence, and the voltage that we get at the terminal is VA1, and that VA1 is equal to going to be Eg minus Ia1 times Z1, meaning the voltage drop that will happen across the positive sequence impedance Z1 because of the positive sequence current Ia1 flowing in that circuit. And on top of that, we must not forget we are drawing this circuit, or we are studying this chapter from the perspective that we want to analyze a power system under fault conditions. So if a fault occurs, we always know that it occurs at a particular point of our interest. Maybe we can just say, okay, if a fault happens at this point, then what will happen? And in real life, it can happen anywhere in the power system. So that fault point comes into the scenario, and that fault point is also supposed to be there in our sequence networks, and we show them respectively. In positive sequence network, we show it as F1. When you go to negative sequence network, we show it as F2. When we go to zero sequence network, we show it as F0. So if we look at our diagrams, sequence networks, they have all the respective parameters in them: N1, Z1, IA1, VA1, F1, and so on. For negative sequence, it should be N2, Z2, F2, IA2, VA2. For zero sequence, it should be N0, the reference bus or the neutral bus for the zero sequence network, and Z0. So that's how we draw them, and that's the simplest form of all the sequence networks that we are talking about, meaning three of them. But when it comes in our real life, we will have a generator, we will have a transmission line, we will have transformers, we will have loads. The load can be a motor, load can be a static load, like a combination of RLC. So when we will have those, the reactance diagrams need to be drawn accordingly so that we can look at the reactances and then analyze for the current flows and the voltages, and then calculate the volt ampere or the MVA, fault MVA, and all those stuffs. A little bit more complicated cases will be coming when we deal with our real power system, but we will go in such a way that we understand each and every part of it, so that we can apply what we are learning in terms of theory and can solve the power system analysis under the fault condition. So let's go to the first one, which is the sequence network for series impedance. And in most of the cases, we get series impedance in our line, because even if we imagine that we have a simple generator, three-phase generator, and we're connecting a three-phase load across it. Let's say that load is a static load. It has just resistance and inductance in it for each phase, and then we are connecting the load and the generator via a three-phase line. That line is nothing but representing a series impedance, because each of those will have some resistance in them and some sort of inductance. The inductance might be very, very small. We can neglect it for practical calculation, but it's still there. So if we generalize it, that there will be some series impedance in the lines that we can consider for our calculation. What will be, or how will those positive, negative, and zero sequence impedances coming into the scenario of fault calculation? So what we do here, we generalize that. We show those impedances for each phase, and they are labeled as ZAA, ZBB, and ZCC. Their voltage drops across them due to the phase currents that are flowing there: IA for phase A, IB for phase B, and IC for phase C. And if the voltage drop is considered, they are labeled as VA to A prime, because the two terminals are labeled as A and A prime. The similar procedure is followed for the other two phases, B and B prime, C and C prime. Of course, we must note that we also considered a neutral line here. So all those phases will have their respective phase voltages: V to A to N, B to N, and C to N, and so on. So if we consider this network I'll go through the mathematical derivations. It's the same like what we did in the previous case. So what we do, we write down the equation considering the voltage drops and putting them in matrix form. So the VAN minus VA prime N. So this is the voltage drop across this impedance ZAA, which is labeled as VA prime. The same thing for phase B prime. For phase C, it will be C prime, and then we'll find that it will be coming as like this: ZAA, ZAB, AC, AB, BB, BC. Again, we find that diagonal feature here, they are representing the self part of it, and the others are mutual between between A and B, between A and C, between A and B, between B and C, between A and C, between B and C, whereas the diagonal is the self impedance and the currents are there for the respective phases. So if we go there to what we did, that this is the phase voltage and it's actually the product of the phase impedance and the phase currents. So ZAVC and IAVC are the phase currents. Then we will do that symmetrical component analysis. We knew that formula. How do we put it from actual phase voltages, actual phase currents to positive sequence, negative sequence, and zero sequence components? So we put them in this format, and if we assume that there is symmetry, meaning ZAA, ZAB, and ZAA, ZBB, and ZCC, they are same, meaning they are balanced impedances are there, and in between the phases, meaning between A and B, B and C and A, they are there, but they are also same. So then we will arrive to the condition that all the off diagonal elements will become zero, whereas the diagonal elements can be represented now by Z0, Z1, and Z2, because we want to see them in terms of positive, negative, and zero sequence impedance. But Z0 is not going to be equal to Z1, but Z1 is equal to Z2. So what we'll find that Z0, the zero sequence impedance, is the sum of those two impedances, ZAA, meaning the self impedance of that phase A, and the mutual impedance between A and B times 2, whereas Z1 and Z2, they will be same, and they will be also the sum of those two impedances, ZAA and ZBB, but in this case ZAA minus ZAB. So that's how we do it, and we see it from these two equations here, that when we have series impedance in our power systems, we will have three impedances: positive, negative, and zero sequence impedance, Z0, Z1, and Z2. But Z0 will be different from Z1 and Z2, whereas Z1 and Z2 will be equal to each other. Now we go to the next step, considering if the mutual impedance between any phase A and B, B and C, and C and A are not there, then what will happen? We'll find that Z1, Z2, Z0, they are all going to be the same. So it's a condition: if the mutual impedances are not there between the phases AB, BC, and CA, then we will have Z0 equal to Z1 equal to Z2. All the three sequence impedances will be same. But if the mutual impedance is present, then Z1 and Z2 will be equal to each other if ZAB, ZBC, and ZCA are the same. So we need to remember that part, and from there we can draw the sequence networks. We saw for zero sequence, V0 is the voltage, I0 is the current, Z0 is the impedance, and we show the impedance value here, which is ZA plus, let me make it a little bit bigger, ZA plus 2ZAB. For positive sequence, the voltage is V1 and Z1 is the positive sequence impedance, and the equation is ZAA minus ZAB. For negative sequence, it's also the same. I2, V2 are the currents and voltages. Z2 is the impedance. This impedance Z2 is equal to Z1. So we will have to draw the sequence networks for each of them. We have the equation, so if we forget any of them, we can always go back and draw it from there, either from the equation to the network or network to the equation. It's not difficult, just what it needs is that understanding of the process. Now I go to the transmission line. It's similar. Again, we have a three-phase line. A, B, C are the phases, and then we have the neutral as well, which is shown as grounded. So the neutral current will be flowing here as I neutral. IN is the neutral current, so it's the sum of all the three phase currents, IA, IB and IC. And then we label them accordingly: A prime, B prime, C prime. Voltages are there: VA, VB, BC, and also the respective phase currents or the line currents. So IA, IB, IC are there, and the impedances of each phase ZA, ZB and ZC. On the neutral there is also an impedance which is Zn, and mutual impedances we assume that they are same in between the phases AB, BC and CA. So they all are same, and we assumed as Zm. M is for mutual impedance between them. So if we consider it's the same thing, we consider the equation of neutral current, then we apply the Kirchhoff voltage law. All the voltage drops are considered, so the impedances are coming into the scenario along with the respective currents. So we can write the three voltage equations for phase A, phase B and phase C. You just have to look at them when you have a little bit free time. We put them in matrix form, and that is what we get here. And again, we can look at that something is happening here in terms of the diagonal, that Zs plus Zn and Zn plus Zn, they are becoming same. And if we put them in compact form, like the voltage is equal to the product of the phase impedance and phase currents, then it will give rise to those conditions. If we apply the symmetric component here from phase to sequence component values that we have learned earlier, then we will finally, after doing this manipulation, we will find that it will become like this. So sequence component impedance is 0, 1, 2 for the impedance will be like this. Off diagonal elements are not there, meaning they are 0, and positive, negative and 0 sequence components are there. So 0 sequence component, negative, positive and negative sequence components are there, and they are same, but the 0 sequence component is different, and they depend on not only on the impedance of the phase, they also depend on the mutual impedance. They also depend on the impedance in the neutral. So we find that it can be two different impedances. One is for 0 sequence and the other one is for positive and negative. And the mutual impedances, if they are not there, then it will get reduced in terms of the 0 sequence value. And if we have no impedance on the neutral, then we might find that positive, negative and 0 sequence impedance will become equal to each other, giving one value for three of them. It's that same condition that we considered earlier. So either we will get two different impedances, or we might get one equal impedance for each of those three component impedances. So again, we draw the diagrams coming here. A0, IA0, Z0 for 0 sequence, VA1, IA1, Z1 for positive sequence network, and for negative sequence network it will be VA2, IA2 and Z2, and this is the other side terminal voltages. Again, this is the simplest form of the sequence networks. So if we go to the next one, which is the rotating machine, a synchronous machine, if we consider, so we will have three different values: positive sequence, negative sequence, and zero sequence. And also, like I mentioned, it depends on the time duration of our interest, if we are doing a transient study or subtransient study or a steady state study, and the impedances will be different. So for subtransient, if our interest is only for one cycle means the time taken to complete one cycle corresponding to that frequency of operation. If it is 50 hertz, it will be 20 milliseconds. So if we want to see what is happening within that 20 millisecond time, then we will consider it as subtransient study. And then the positive sequence impedance Z1 will be only subtransient d axis xd. This for d axis we also have another thing, xd and xq quadrature. So we will use that subtransient reactance only. If we are considering a time duration of 3 to 4 cycles, a little more than one cycle, we call it transient study. For a short duration, but not as short as one cycle, so we'll use transient reactance x prime, and they are labeled like that always. So if you see somewhere it's xd, it's reactance, steady state reactance of the generator of the winding. But if you see one prime is there, two double prime, meaning is subtransient. So the positive sequence impedance will depend on the time duration of our interest. Are we doing a transient study or subtransient or a steady state system? So that will come there. But for negative sequence impedance is completely different. We also need to consider the quadrature reactance. So the xq, q is for quadrature, and we take the average of that. So negative sequence impedance is completely different from the positive sequence reactance. And then we come to the zero sequence reactance of the synchronous machine, and it depends on something completely different. First of all, the zero sequence impedance of the machine, when the machine is being manufactured, how the windings are being laid out across the 360-degree of that stator winding, and then how we connected the stator winding neutral. When we have a three-phase generator, we will definitely have a star connection for generators, and then how we connect that star connection, meaning the neutral point, to the ground. So the type of ground is important. Like we saw some example that we can leave that star point or neutral point as a floating one, meaning that point is not connected to the ground at all. Next, what we can do, we can connect that neutral point to the ground using a piece of wire for which the resistance of the impedance can be neglected, meaning its impedance or resistance is very small, meaning short circuiting the neutral point and the ground, meaning solidly, we call it solidly grounded if the resistance or the impedance of the neutral and ground connecting wire is negligible. Sometimes we can put only a pure resistance, although it might not be a pure resistance, but some inductance will be there. So meaning some impedance is there in the connecting wire in between the neutral and the ground. So that is another option. Sometimes we connect the neutral point to the primary winding of a transformer, and the secondary winding of the transformer is grounded, and it also done for transformer as well, for big transformers. So the type of grounding will come into the scenario. Not only this type of configuration, meaning leaving it floating or connecting the neutral and the ground using a piece of wire for which the impedance can be neglected. We can put an impedance in between, we can put a transformer in between the neutral and the ground. But also we also need to consider those impedances that are appearing from the connecting wire or the transformer can be classified as low impedance or high impedance ground. meaning impedance might be small, impedance might be high enough. So the configuration as well as the value or the magnitude of the impedances are also of importance when we think about the zero sequence impedance of a synchronous machine which is rotating in nature. So when you go to draw the diagrams, we show them like this. This is the positive sequence network. If you remember that, we are going to show them in terms of the Thevenin's network. A voltage source will be there along with the respective current and impedance for the positive sequence. And then for the negative sequence, there will be no voltage source, but the impedance and currents are there. And if we go to the zero sequence network, again the voltage source is not there but the impedances are there. But one important thing to note in terms of the neutral and the ground connecting wire, the impedance of the wire Zn is normally the symbol that we use to represent the impedance of the wire that we use to connect the neutral and ground, Zn. But when it comes to the zero sequence network, it is multiplied. For static ones, we saw that it was multiplied by 2, but for synchronous machine rotating device, it is multiplied by 3. And for transformer, we also will see something like that. So it's multiplied by 3. We will also have to remember that a little bit. And how it comes like that, we can see the equations, how it comes like that. I skip those equations here a little bit. Just to keep it simple, but we will have to remember that whenever we need to draw the zero sequence network of a generator, we will need to consider the neutral and ground connecting wire and its impedance, and then it has to be multiplied by 3 added with the original zero sequence impedance of the machine, which is Z0G. So that will be the zero sequence network for the generator. Now the one which I need to go is the zero sequence network of transformers, and this one is also not that straightforward like series impedance or transmission lines, because it's different, because we can have 3-phase transformers in different configurations. And different configurations is what? We can have a transformer winding configured as star or delta, and again those star points can be left floating, connecting solidly to ground, connecting to ground via an impedance. So all those things need to be considered for that particular connection type. And when we do so, we cannot forget about the fact the transformer operation is very much dependent on what is happening on the secondary side. Meaning, if we connect the primary side of a transformer to a voltage source, what will happen? Immediately? It will cause some current flow in the transformer, setting up the magnetic field and inducing voltage on the secondary winding of the transformer. Also, some voltages will be developed across the primary winding, and the current flow in the primary winding will be dependent on the applied voltage and the voltage developed across the primary winding and the impedance. So we will get no load current if the secondary winding is left open. If we leave the secondary winding of the transformer open, then we will get a current in the primary side of the transformer, which we call as no load current. We label it as, or show it as I0. So that's the no load current, and we know that no load current is very small as compared to the full load or the rated current of a transformer. Is very few percentage, 1 or 2%. But that no load current actually does a lot of things, or it sets up the magnetic flux, and all those things also supplies a little bit of losses in the transformer. Now, when we connect the secondary side of the transformer, then secondary current I2 will start flowing, and because of that secondary current I2, there will be increase in primary current. Now that primary current will have another component, and that component can be called as a reflected component of the secondary current to the primary, and it will depend on the ratio of N1 and N2 or V1 to V2, whatever you call it, transformation ratio or turns ratio. So if you have a 5 ampere current in the secondary side, how many amperes you will see on the primary side will depend on N1, N2 or V1, V2 for the rated voltages of the transformer. So we'll see that reflected component of the secondary winding in the primary. Now in the primary we still have that no load current I0. So these two currents now to be added vectorially and will give rise the final value of the primary current. Is that clear to everyone? It's just a reminder, you should know it from the very beginning when you started transformer, studying transformer. Is that clear to you? Anyone can confirm, or if I'm missing anything, or if you know something more, you can tell me. If you have any question, please ask. Can you confirm that you understand this part, the currents of the transformer from secondary side to the primary side, and then that current will be added to the no load current of the transformer to give us the final value of the primary current. Can anyone please confirm?
I'm sorry, sir.
Yes.
So you purposely remove the load from a transformer. You replace it with open circuit.
Yeah, we can do that.
And this is done only for the zero sequence network.
This is only done for
The zero sequence networks.
No. In practical life, it happens. It's not for zero sequence purpose. What I just was talking about just now is it can be done anytime, anywhere. It doesn't really need to be done for the zero sequence purpose, but that actually has some impact on the zero sequence, which will come.
Okay.
Like you can just take a transformer and apply some voltage to the primary winding, and your secondary winding is left open. Let's say we have a transformer in our real life in distribution system, like all our houses or premises. It doesn't matter where it is, commercial or educational or municipal or agriculture or at homes. All those connections that we get, it's coming from a transformer, distribution transformer. So let's say there is a transformer which has one outgoing line, three-phase line, one outgoing three-phase line, and that is supplying an area where there are a number of houses or premises, commercial and all those stuffs. So if something happens to the transformer, let's say that transformer is now got broken on the secondary side, no connection. Secondary is isolated. We use isolators like manual in olden days. Still they are there, those manual isolators. So we isolate them. The secondary side is open. And now what we need to do to fix that problem, we come and check and all those things. So when the problem is fixed, then we supply the primary. We still keep the secondary open. We check the voltage because we want to see if the transformer is operating. If we apply this much of voltage at the primary winding, how many volts we are supposed to get at the secondary side, meaning the secondary is left open because we have not connected that isolator yet, or a switch, whatever it is. So the secondary can be left open at any condition if we need to, but we don't switch off unnecessarily unless we have to do it like for load shedding. So when they do the load shedding, they actually switch off. The secondary side is open. Also, you want to do it for primary for the purpose of protecting. If you still want to take the opportunity to do some maintenance during that load shedding time. We also do that kind of activities. Like I know that there will be a load shed for 2 hours, so I knew that their transformer was having some trouble, so let's take that opportunity to do some maintenance in the 2 hours and we'll fix that. So the point is that we can leave the secondary open, and we also can apply loads as we need or as we would want. So the point is that secondary current comes as a reflection to the primary and get added with the no load current, and then we get the final value of the primary current. But I mentioned that no load current of a transformer is very small as a percentage of the full load current. So let's say if it is 1% and the primary current is coming from the no load current and the reflected component of the secondary current. So if we neglect that 1% or 2%, so most of the primary current is coming from the secondary current. So now the thing is that if we leave the secondary open, there will be no secondary current. I2 will be equal to 0. So if there is no secondary current, there will be no reflected component of the secondary current on the primary side of the transformer. Is that clear? If we neglect the no load current I0.
Okay, thank you, sir.
So if we neglect the no load current I0, and if we find that there is no load, meaning the secondary is left open, there will be no reflected component of the secondary current on the primary side. And that will be useful now for us. Because if you remember, when you started looking at those delta connection, star connection, if it was a delta connection of three-phase windings, what we saw that within the delta legs of phases, zero sequence currents will be flowing, which will be equal to each other in magnitude, and they will be parallel to each other because they are zero sequence currents, but there will be no line currents flowing in terms of zero sequence currents because it's delta connected. We also saw something similar, that if we have a star connection of 3 windings and the star is not grounded, then we will have no phase current, no line current in terms of zero sequence will be flowing in that star connection. Now that is coming here because if we have a delta connected winding in the secondary side, so no zero sequence current can flow in the line. If we have a star connected winding in the secondary side for which the star is not grounded, no line current in terms of zero sequence can flow on the secondary side. So if there is no current, zero sequence current can flow in the secondary side because of delta connection, because of star connection with neutral not grounded, then it won't have any reflection on the primary side, and that will impact on the reactance or sequence network or reactance diagram. That's what we are trying to say. So let's consider this star-star connection transformer. The primary is connected as star, the primary star or the neutral point is grounded solidly. This diagram symbol, it has to be understood as well. The connection here to the ground shown is representing that the star or the neutral point is grounded solidly. If there is an impedance, we will have to show the impedance or the reactance in between the neutral point and the ground. But if we look at the secondary side, star connected, and again we'll have to understand this symbol. It means it's star connected, but the neutral point is not grounded. So this is the secondary side, and it's star connected, neutral not grounded. What does that mean? Zero sequence component of current cannot flow in the lines. For this secondary, zero sequence component of current cannot flow in the lines, and if it is not there, then it won't have any reflection on the primary side. And then what it makes us to do, when we draw the sequence network, we'll have to show the respective phase, reference bus, the incoming terminal, outgoing terminal, the impedance, zero sequence impedance. And as secondary side is star connected, neutral ungrounded, no zero sequence component of current can flow in the line, and hence there will be no reflection on the primary side. So current actually cannot flow on the primary side as well. And How do we represent that current cannot flow on the primary side? By showing an opening. This is the opening, meaning the current cannot flow in the primary side. And this current we are talking about only zero sequence current. We are not talking about other sequence currents at all. We are only talking about zero sequence currents, because for transformers zero sequence current is different because of the configuration, because of the connection of the neutral to the ground, how it is connected, if it is connected to ground at all or not. So we see that although it's star connected grounded, there is a way that zero sequence current can flow because it's star connected grounded, but it's the primary. The primary has a current that comes from the secondary. So if there is no way secondary current can flow, there is no way that current will come to the primary. That's why we used to show an open in the reactance diagram. Similarly, if we take another example, we have a star connected, neutral point is grounded solidly to the ground, and the secondary side is delta connected. So if the secondary side is delta connected, means what? Within the delta legs, zero sequence currents of same magnitude will be flowing within that delta, but in the lines there will be no zero sequence current that can come. So same thing will happen here. So we cannot see any reflection of secondary current onto the primary. So how do we do that? We draw it like this. Because it's star connected grounded, so it can flow to the ground, but from the secondary side there is an opening here as well. So it will now be important for us to look at the connection of the transformer star and delta, and if it is star, we will also need to look at how the neutral is connected to ground, if it is connected to ground at all or not. So if it's not connected to ground, is no zero sequence current can flow. So we'll have to consider all those things. So for that, it's very difficult for us to remember and analyze when we're drawing these reactance diagrams, and it takes time. So what was done by people, the scientists or engineers, they made it simple for us. They said, we know that we can represent a transformer by primary and secondary winding and an impedance between them. And we don't need to remember that primary winding and secondary winding impedances separately. If you remember when we are talking about the power unit, because it becomes only one impedance. If you are talking about primary impedance, secondary impedance, and you did those calculations in other modules, you convert those primary impedances to secondary, and you can see what is the impedance viewed from the secondary side. You can do the opposite as well. You convert the secondary impedance to primary and add them, and you can say this is the impedance referred to primary side of the transformer. But when we go for per unit, it's one impedance. They will be the same for primary and secondary that we discussed in Power Systems 1. So that impedance is now going to be shown here. And what impedance we are talking about? We are talking about zero sequence current. So zero sequence impedance is in the picture, not others. Others are easy. Positive sequence and negative sequences are easy as compared to zero sequence. Zero sequence is much more complicated as compared to the other two. So we show that impedance here. Of course, the other impedance will come from that connecting wire between the neutral point and the ground. I'm sorry, I'm taking few minutes more, but I just want to finish this slide. The other parts I can continue tomorrow. So we show that impedance here, the primary side and secondary side, and these are some 4 switches here. These 4 switches are there. If you see them, the one here which I'm pointing to, A and B, they are the series switches, because you can see it's in the series, and these 2 switches are the shunt switches of parallel. They're connected in parallel, series and parallel, series switches and shunt switches. So looking at the star connection and delta connection, looking at the neutral point, if it is grounded or not, and if it is grounded via some impedance or not, we can draw the sequence network very easily. That is what we are going to show tomorrow for many different configurations, and it becomes very easy following these steps. If we have delta connection, what we must do, If we have star connection, what we must do? If we see that star connection is grounded solidly, what we must do? If we see that star connection is grounded via an impedance to the ground, what we must do? So we'll do that tomorrow. Please ask any question if you have. Any question from anyone? Hello, how are you all? No question. Let me give you 1 minute to think about any question. Did you understand what I was talking about today?
Yes, sir. I understand. But sir, this is only for transformers. So
This one is only for transformers. Series impedance we talked about, it was separate. We found that Z1 is equal to Z2 and Z0 is different. We also did the transmission line. We also found the same thing. Z1 is equal to Z2, Z0 is different, but they can become equal on those special conditions if the phase impedances are same and also the mutual impedances are same. But for synchronous machine, we saw the positive sequence impedance is different and it depends on the time duration of interest. If it is subtransient, we use subtransient reactance. If it is transient, we use transient reactance. If it is steady state, we use steady state reactance. The negative sequence impedance is completely different. It uses the average of XD and XQ. So XD plus XQ by 2. So that's the negative sequence. And zero sequence impedance of the synchronous machine is dependent on two things. First of all, the zero sequence impedance of the machine winding. Second, the type of grounding. Are we grounding the neutral solidly or leaving it open via some impedance, via some transformer? What is the value of the impedance or the range of the impedance? So that's for the synchronous machine rotating device. Now we're coming for the transformer. Is different as compared to the series impedance transmission line, rotating machine like synchronous generator or a motor. For transformer, star delta, we don't get this type of thing. For none of them. For the generator, we don't get star delta. It's only star connection. For transmission line, it's simple. Series impedance, the same thing. So that's why transformer one is different and is so important. We cannot avoid any transformer and thinking of operating our power system, and they will always be there. It immediately starts up at the generator at the generating stations to step up the voltage. Then we put the transformer to step down the voltage to distribute it to another level at lower voltage. Again we step it down until we get to the lowest voltage like 230 or 220 here in South Africa, in India. In other countries they use 120 as well. Yeah, so for transformer, this is only for transformer, but we must remember there are two series switches, two shunt switches, which will help us to draw the reactance diagrams for the zero sequence only, not positive and zero negative sequence. Those are easier as compared to zero sequence network. Is that okay?
Yes, sir. Thank you.
Thank you very much. Keep well. Have a wonderful afternoon. We will continue tomorrow.